Yeah, so welcome everyone to session 4, the one before last. So last time when we talked about, axiomatic system and universal systems of truth, and we said if we started off with some alphabet, like this one, for example, you have the number 0, you have the successor operator, which you can use to define 1. 1 is basically the successor of 0, and so on. The negation for all, there exist, and so on. You have all these symbols which you can use in order to describe statements of interest. This alphabet is finite, obviously, and we accept a set of self-evident truths, just like those self-evident truths that we saw in our toy example, the addition system, the PE hyphen. In addition, we accept some defined rules of derivation, rules by which we can go from a statement to another statement. We start from the axiom and we derive something that is also true, and we derive again and again until we arrive at some statement. And the question is, the first question, the first major question that we were trying to find an answer for, and mathematicians in general were trying to find an answer for, is this language complete? Can this language express every possible true statement out there? And we said that, when we say truth or problem or computations, these are all the same thing, basically. And the second question is there a guarantee that no false statement could ever be arrived at by valid applications of the rules of derivations? So the system is airtight. It cannot mislead us into asserting that a statement is true when it's in fact false. And that is called consistency. And the third question is there a guarantee that every true or false statement can be determined directly by unambiguous mechanical applications of the rules of derivation? So we call this decidability. So the first two property, completeness and consistency, this relates to the language that we are using. The language that we are expressing is this alphabet to express our truths, our statements, etc. While decidability is something that relates to those mechanical instructions, or what we call machines, or proofs, or algorithms. All of these are the same thing. So the reduction that we saw last time, the Gödel reduction, answered the first of these two questions, the question about completeness and the question about consistency. So what we did last time, we said we will start with an encoded alphabet. So whatever alphabet we have chosen, for example, the Russell-Whitehead set of alphabet that they were using in that massive volume, foundational volume that they were hoping would define, would provide a foundation of mathematics from an austere minimal set of logical primitives, like the thing is equal to itself, or two things that are equal to the same thing are equal to themselves, etc. If we start with that system, for example, or any other system, the first thing is to abstract away that system. We encoded it using numbers, ID numbers. And remember, the set of the alphabet is finite. And then we arithmetize the statements into unique integers by raising every symbol in the statement to the prime, to the nth prime number, which guarantees that every statement will have a unique number. This is true by the fundamental theory of arithmetic, the uniqueness of factorization of prime numbers. And then we further arithmetize proofs, which are nothing but a collection of statements, a series of statements, using the same strategy. We raise the first prime number to the number that we got in step 2 for that statement, second prime to the second statement, and so on, until we arrive at the end to a number, a unique number for that proof. And finally, we constructed a meta statement, a statement about statements in the system that cannot possibly be proven within the system because of that weird self-referential thing. And today we will see again that we will, use this self-referential notion in order to prove something about decidability as well. So this Gödel reduction is one of the most important results in the history of human thought, but potentially, and as I mentioned, it's it dealt a blow to the dream that we have a universal mathematical system that no true statement out there can escape and no false statement out there can get into. We did not go through the proof of the impossibility for the system to prove its own consistency, but as I mentioned, it follows very easily from the first one, namely that the problematic statement that we showed last time that cannot be proven within the system, even though it was expressed correctly and using the axioms of the system, assuming that the system is consistent, meaning it cannot produce a false statement that is misleadingly appearing as true. If we make that assumption, we arrive at a contradiction that such a system must contain a proof to that problematic statement. This is what Gödel showed in his second incompleteness theorem, but we did not go over to skip that one. So today we're going to go over the third property, which is decidability. And again, decidability is a property of algorithms or machines or proofs, basically. Generally, I don't like to use the word proof because algorithms or machines is in fact a generalization of the classical concept of mathematical proof. And as we will see probably next time, the notion of mathematical proof in the classical sense, Pythagorean theorem, for example, it belongs to a special class of computational problems. So while there are the computational problems outside of that class, so the notion of algorithm is way more general. Just to give you intuition, since I mentioned this now, if you think about Pythagorean theorem, for example, it will be given to you in a series of statements, right? Which end with the statement that x squared plus y squared is equal to z squared, for example. And that's the true statement that the system is telling is true. And the algorithm that decides whether that statement is true will start from the axioms, and it will keep driving every possible statement, okay, every possible statements of length 1, for example, and then 2 and 3, and it will keep enumerating until it reaches the massive set of statements that contain the same length, that are of the same length as the Pythagorean theorem. And it will tell us, yes, there is a path from axioms all the way to the statement, therefore accept, or is true, or print yes, for example. And so, in fact, just to give you a hint, you can think of the classical notion of mathematical proofs as exactly the same class that the problems we covered, 3-SAT, knapsack, etc. The same class, it belongs to the same class as that one, which is a subset of all possible statements out there. There are computational statements that are much harder and belong to a higher class than that one, for example. For example, the set of all possible series of moves that lead to white capturing the king of black in chess, for example. That is also a series of statements, and it is a proof. And as we will see probably on Friday, that that statement belongs to a higher class than the restricted class of the classical notion of mathematical proof, basically. To clarify this further, and I hope I'm not confusing it further, but when you are looking at the Pythagorean theorem, for example, at every fork in the road, yeah, there is a huge but finite number of possible paths that you can take from there, right? From a true statement, there is a bunch of other statements that you can derive it from. And so you pick one of them. If it leads to the Pythagorean theorem, that's good. If not, you backtrack and you try a different combination of the alphabet, for example, until you arrive at it. So from a decidability point of view, the classical notion of proofs is exactly that the classical, the computational class of that 3-SAT, knapsack, etc. belongs to. Okay. So we are done with truths. Now we are in machines or proofs. And the question we're asking is there a universal, capital U, a universal machine? That means an all-powerful machine that will decide every possible language. So this universal machine has two properties. It is aware of the axioms of the universal language, and it's faithful to the rules of the language. Doesn't make any mistakes. Very important to notice that the axioms and the rules, they are finite and they're unambiguous. And notice here that I'm using universal language with small u, because we already decided that we don't have universal language with capital U or absolute. So there is nothing special really about this machine that we are trying to decide whether it exists or not. Right. When consulted with a statement, which, as we saw last time, can be encoded itself as a number, it will decide, does this number belong to the set or not? Does it belong to the general set of all truths, all possible truths, or does it belong to this specific, a specific set of truths, for example, the set of computational problems that the SAT, knapsack, etc. belongs to, etc. So it's just deciding in or out mechanically. And yeah, I'm reminding you here of that mission, that simple language that we came up with for arithmetic, and how we can decide whether it's in or out. Last time I sketched a rather inefficient algorithm that generates every possible statement that has the same length of the proposed statement, the PE- statement. And then it loops over that container, and if it ever stumbles upon the statement, the input statement, it will say yes, it is true. If not, if it exhausted all of them, it will say no. That algorithm was inefficient, but I did that intentionally in order to show you how mechanical, how dumb, or how basically no intelligence required, basically. So does this universal machine exist? So we settled, as I said, we settled for a universal language with small letter u, that cannot be ever complete and consistent, regardless of the axiomatic system we choose. And we're going to ignore those logical black holes that we arrived at, just like the Gödel statement that cannot be proven over the system, which, as I said last time, you can think of it as the liar's paradox. You can think of it as a mathematized version of the statement Socrates says all Greeks are liars. If it's true, then it's false, then it's false, then it's true. It's a self-referential problematic statement. So we're going to ignore statements like that. And by the way, just for FYI, that's not the only statement that is beyond provability. There are quote unquote natural statements that also cannot be proven within any axiomatic system. I mentioned last time, I believe, the Paris-Harrington theorem. You can look it up as an example of a non-contrived statements that cannot be settled into the truth or falsehood camp. You might be curious, since the result of Gödel, what are people using as, what have we settled on as a system to express our problems and our truths, our machines, everything. Remember, the axiomatic system describes everything. And that is something called ZFC set theory. It's a set theory with 13 axioms, okay, with the assumption or with the wink-wink agreement that those logical black holes, we'll just ignore them. In practice, we don't run into them. We will just gonna go, we're just gonna ignore them, and we will use set theory with these 13 axioms. And in practice, we have no issues. It's not like we are stumbling upon a logical black hole every day. In fact, in the first two sessions, when I introduced those problems, 3-SAT, knapsack, etc., the symbolic representation that I presented them in, it is in fact using the alphabet of this language. And it's the most familiar language. Regardless of the domain you guys are coming from, you probably used it yourself without even knowing. Okay, so now we are thinking of the universal language as all truths minus those problematic statements. Just gonna ignore them. And again, the universal language describes anything in any domain, which is indeed the case. ZFC set theory is used in all domains. And now we're going to look at decidability. So assume, don't forget, as always, we are thinking about truths and proofs in that very clean, very minimal way of numbers. We encode, regardless of the alphabet, we encode it as numbers, and now we can think of both of them as sets of natural numbers. So keep that in mind. And also keep in mind that when I talked about set theory, I told you it's a finite means through which we can talk about infinite objects, right? So assume that we have encoded all our languages and all our machines. We talked about this last time. A machine itself can be encoded as a number as itself. It's written in whatever. It's described in pseudo algorithm using set theory, for example, or it could be described in Python or whatever it is. We're going to encode it into a number itself. And then we order them lexicographically somehow. They are both infinite, obviously. So every machine and every sentence is encoded. And what this says, in this infinite enumeration, what this says, it is the result of applying machine number 2 with the statement number 2, the second statement, or more precisely, the statement encoded with the number 2. Okay, so now consider a machine K, which operates as follows. It receives a sentence N as input. It feeds sentence N to machine N. So the kth machine uses the nth machine as a sub-procedure. Okay. Or think of it as, machine N is a function that is called by machine K. Sub-process function, etc. Same thing. And then whatever the results that the nth machine returns to K will just add 1 to the results. Okay, whatever even if that makes the result gibberish or makes it incoherent, whatever it is, it will just mutate the result of machine N, which applied to its own number. Now, machine N, for probably the vast majority or all of the machines, okay, that we feed their own description into them, the results is probably meaningless. It doesn't mean anything. Okay, but we don't care about that. We're just talking in abstract terms here. Whatever the result is, it could very well be that every machine, when the input given to it is its own number, the machine may very well just do some nonsensical stuff and then print something. Whatever that thing is, we're just going to mutate it. We're going to add one to it. And that's actually equivalent to, if you think about it, it's the diagonal plus 1. Because we're taking machine n, machine 4, and we are giving to it as input the number 4, its own description. The number 4 is an encoding of the description of machine n. And then K just stops, basically. So K is kind of like, is doing mischief here. It simulates machines on their own descriptions, and then whatever those machine results in will just print something different. It's just like adding 1 to it, for example. So if we put this symbolically, the kth machine takes n and then feeds it into, as a sub-procedure, as a sub-function, it feeds it into the nth machine and then adds 1 to the results. This is what K does. Now, what happens if we supply the sentence K to the machine K itself? What we get is this. The kth machine, when supplied with K itself as input, K is the number encoding the kth machine, is equal to mk of K plus 1, which is obviously problematic. This statement cannot be true. It is yet another black hole, logical black hole that we stumbled upon. Which means what? What does this mean? It means that our initial assumption that for every language out there, there is a machine, there is a way for us to enumerate every possible language in some encoding, and a way to enumerate every possible machine in some encoding, and this table will be true. Like, this table exists. Every possible dot here is computable, decidable, basically. We started from that assumption. So now when we arrived at this logical black hole, it means that our initial assumption must have been false. Machine K could not have existed. Notice here that we are arriving at these logical black holes using self-referential thinking. It has been the case in every possible roadblock that we have stumbled upon, starting from Rasul paradox, which dealt a blow to naive set theory, and then Gödel results, which also contain self-reference, and now with decidability as well. Notice here that we didn't even define, we did not have to define the internal of the machine itself, the MK which accepts other machines. We did not even have to take a talk about the details of it. We just logically arrived at this logical black hole, speaking of it in abstraction, MK, assume that such a machine exists. So this decides our last questions regarding the notion of universality. There are more languages than there are machines to decide them. Okay, so we came across one such a language. It's a language, it's the language, which contains all the outputs of all possible machines plus 1 to it. So these two questions, which we have covered so far in these 2 sessions, they are questions about the foundation of mathematics itself. And computer science itself, it was born out of the answers to these 2 questions, right? And this was in the 1930s when concrete manifestations of computing machine has not yet existed. The word computer back then, it just means a human, typically a woman, that is crunching numbers. So you might have seen some images in World War II where a large hall of women are doing calculation in order to determine something about the enemy's airplane movements, things like that. Again, this is not Russell, but it's the actor Sam Elliott, which I imagine is playing Russell in a movie that would cover talk about that period. So unfortunately, the dream for these three properties turned out to be the answer to these three questions turned out to be the negative. And it was a humbling thing, but it's a humbling thing, but it's also a good thing. It gave us a place to know. It allowed us to know our place, right? In this, when we started off, the notion was still a bit vague, and the questions were extremely grand. Is there a universal system of expressing all truths, and is it complete, consistent? The problem seems at its face very intractable. So the answers kind of clarify for us where we are, our place in the universe, basically. And of course, the answer to these questions, as I told you, had huge implications. So Gödel decided the first two, and Turing was the one who decided decidability, the one who gave us that negative answer. So that takes decidability. Of course, the machine MK that I told you is not the only machine. It's contrived, and we use it to arrive at an answer regarding decidability. But then, of course, there are other non-contrived statements that cannot be decided. One of them you probably heard of is the halting problem, which says for arbitrary k, print yes if the machine k halts in every input. So that's another example of something that is undecidable. And there are other quote-unquote natural problems or practically useful languages, yes, that cannot ever be decided. In both cases, the yes and no. There are languages which can be decided in the yes case, but the no case is undecided. For example, the halting machine problem. So just as I mentioned, there are natural statements that cannot ever be proven within any axiomatic system as true or false, like the Paris-Harrington statement, for example, is very natural. It's a very practical statement that we need the answer of for practical reasons. And it's not as arbitrary and contrived as the Gödel statement that we constructed. Same thing in decidability. There are indeed natural problems that cannot be decided. Okay. So now we have, this is the universe of all possible truths. And black here, I'm using black here to signify subjective truth, which, as I said last time, we're not going to go over. But they can be discussed in the philosophy department or place of worship, for example. But as far as mathematical truths are concerned, we now know that there are truths beyond provability, regardless of whatever system we have, that they are beyond provability. And the pink line here, you can think of it as the set of statements that can, in principle, be decided yes, that can, in fact, assume this is ignore I said it's not decided, can assume a truth or value, including statements such as machine M halts at every input, that is a machine, that is a statement that is not beyond provability. It is beyond decidability, but it's not beyond provability. But the black line is the ones that delineates the statements that can be decided as well. They are within the reach of provability, and they are also within the reach of decidability. So for all practical purposes, this is the one that we care about. Okay. Once you go outside of this, here, in this area here, probably the only people who care about are, people who are looking into the computability theory, for example. And here, this is probably meta mathematics. This is what people, working on the foundation of mathematics itself or thinking about mathematics itself. And outside here, this is the philosophy or theology. So from now on, we're going to be inside here. These are truths that can be, that are within the reach of probability and decidability, and they can, well, we can guarantee the notion of consistency about them as well. So we call this the boundary of the provable. Okay, what's inside it is decidable, provable in principle. And we can now ignore everything outside and start thinking of useful things like deciding, okay, how much work do I have to do to decide whether a statement is in or out, a statement is true or false. And as you already probably know, some statements like arithmetic, they are super easy. Is 5 plus 4 equal 9? That is an easy thing to decide. We saw last time a bunch of statements. This 3 sat instance is satisfiable. That is also a statement which we encoded. It's a number and it belongs to an infinite set of natural numbers. Remember the counterintuitive thing we talked about infinite sets. Each one of these sets contains an infinite number of statements, which is a subset of the natural set of natural number, but it's equal to it in cardinality. Some problems are much harder, like protein folding, for example. When you think about it in a generalized, reasonably generalized form, that's hard. Chess is even harder. Chess, as we know it, is harder, but of course, its search space is finite. It's astronomical, but finite. But when we say chess is harder, we are talking about a generalized version of chess. We define it using n pieces instead of 20 or so pieces, for example, and we generalize it and then we prove, oh, okay, this is going to take way more resources in order to solve. So we are beginning to see our place in the universe, and we started with this set of problems. And the reason we started with it is that it is this class of problem is our entry into understanding the initial seeds that led to the whole notion of decomposition of problems into computations and verifications, and they belong somewhere here in this universe. So the complexity hierarchy, okay, each one of these circles, arithmetic is in the middle, for example, because it takes a reasonably low amount of resources. And this one is outside of it. The reason why these mathematical sets are subset of each other, because we say that the machine that is capable of telling us the answer for these is also capable of telling us the answer of arithmetic additions. These problems, they have this property, common property, that the machine deciding them has to make forks in the road every time. And sometimes it might make take the wrong fork, get stuck, doesn't find a solution. The partial solution it builds up to that point is wrong, so it backtracks, etc. So arithmetic is a subset of that, because when you are doing the arithmetic just like we did at school as kids, At every fork in the road, there is only one choice. So it's a special case of this one. So whatever machine is capable of handling this is also able of handling everything. And that's why these circles, they are actually inclusion. This subset of problems like arithmetic, which take easy amount of resources, is a subset of the higher set, which take exponential amount of resources, etc. But I would like you to view this within the context that we have talked about so far. Never forget about this notion. We are given statements written in some axiomatic system, which is encoded into numbers. And the question always is the number in or out? And to computer scientists, this thing is just like the periodic table. And now we don't know about it because computer scientists are not good at marketing like physicists, for example, but also because physics is much older than computer science, and it's, it's taught at school, for example. So up to today, for example, this notion of complexity theory, computability, etc., they are not taught at school, even though they are as foundational. In fact, if you think about it, complexity and computability theory, they do not presuppose anything except basic logic. They do not presuppose anything except the foundational theorem about incompleteness, inconsistency, and undecidability. While physics, of course, we say that something is true or false because it agrees with experiments. There's nothing logical or universal about it. So this object that you see here is way more foundational than periodic table. So it's, yeah. So again, we are, as I told you, we are for the remainder for today, and on Friday when we conclude everything, we are going to pay attention to this circle, things that are within the region of probability and decidability. And we call problems that are easy, we call a problem easy if it takes constant resources regardless of the input, or if it takes n to the power k for some k. So we call that quote unquote easy. I am being sloppy here and imprecise, but that's okay. And we call hard classes if something takes an exponential amount of time, just like the problems we saw in the first two sessions. The depth of the tree in all of those problems, we start somewhere and then we expand. Okay, and we said, there are n steps, and at each step there is two or more. It could even be more than two. And so the total size of the search space is bounded by 2 to the power n, exponential. So we consider that to be hard. The reason why we consider it hard is because, well, if you double the input was 2,000, and then you doubled it to 4,000, the amount of resources grows exponentially, massively exponentially. So we consider that hard. There is another way of classifying problems. Instead of saying simply the number of resources that it takes, we can also say that classes that are decomposable into two parts, a search part and a verification part, and the search part is exponential, but the verification is very cheap. It's logarithmic in the witness size or logarithmic in the, in the input size, etc. That is another way of classifying. It's another way of drawing these circles. And as we will see next time, defining these sets based simply on constants, polynomial, or exponential in the input size will be equivalent. We will derive an equivalent description of that class based on this decomposition. So we will try to take a closer look at all these classes next time. On Friday, we got pushed a little. The order reduction took longer than I expected, so we got pushed a little. And if we start this now, we probably need another hour, so I'm going to leave it for next time. As I said, when we talked about decidability so far, we drew this universe without actually having to know what a machine is. We did not have to agree on what a machine is. When we say something is exponential and it takes a long time or it's hard, are we talking about, you know, the implementation or a naive implementation, or are we talking about an implementation in silicon-based computing, etc.? What are the details of the language by which we measure resources? And we will end where we started, where we talk about this class of problems. And we're going to define it first as the number of, as the infinite set of problems that a machine able to pick a fork in the road can solve them in polynomial time. And we're going to come up with an alternative definition, which is the class of problems for which we can decompose the computation into a search and a verification. And the search can be exponential, but the verification is linear. And we will look at the very first example of having that verification done in zero knowledge, meaning without revealing the witness. So, but even before Friday, you can already get a sense of where we are closing with. In this skit that I shared with you last time, in this first section, I already gave you a sort of a preview of where we are going with this. So the problems that we talked about so far, the 3SAT and the 3SAT, the knapsack, the exact cover, etc., these belong to the same class, which I call here this funny name that pick a fork in the road and backtrack if necessary. This is the class of problem. Of course, this is not the name that computer scientists use to describe that class. They use something much less sexy, like NP. We reduce any problem there in that class to another problem called arithmetic circuits, which is the same thing as SAT circuits, except that we use multiplication and addition instead of and or. We reduce that even further to a system of vectors that are multiplied through. And then we do one more reduction of these vectors. We zap them up into an equivalent representation of polynomials. We add those polynomials, we add them up into one giant polynomial that is equal to 0, if and only if the computation was done correctly. And from this point on, we started with a problem that belongs to that class, and we ended up with one giant polynomial that kind of described all of them. From that point on, okay, what we are going to do is apply tricks from abstract algebra, from probability theory, etc., in order to infer something about that giant polynomial without actually having to compute all of it. And it's after this step that most of the difficult corners of the forest of ZK reside, basically. So this skit that I shared with you hopefully give you a glimpse of what we are ending. But next time we are going to, we will take a closer look at this. We are going to take a closer look at these reductions. And that will hopefully, it will let us understand the place of ZK in this whole universe of all decidable languages, which already, which fits in this general universe of what is truth in the mathematical sense of the word. Okay. So today and tomorrow, the last session I intentionally did not schedule it for tomorrow. I'll leave it for Friday. But it will be just like a conclusion and connecting the dots and making the whole thing fits into. My goal is to have this thing in your head and you understand the place of ZK, where it came from, why it is possible through the notion of reduction. We'll end there. But before that, you already can read this. And you can also go through the CIRCOM materials that we shared. So these are some of the reference materials that I shared with you guys. Now, you don't have to worry too much about the stuff going under the hood for now. Things like pairing or the trusted setup. CIRCOM, of course, is a compiler. It's nothing but a reducer, each one that takes NP statements, general pin statements, pick a fork in the road and see if it leads you somewhere. This is what the CIRCOM compiler does. It's a reducer through these series. You don't have to worry too much about what's going on under the head. All you have to do is be comfortable with CIRCOM, run a few code bases, tinker with the circuits, and you can think of it as if you have done any hardware circuit description using those high-level languages that describe electronic circuits, it's very similar to that. So CIRCOM is the language, right now it is the go-to language for creating ZK dApps, the ZK dApps that do specific things, and our code base on Wednesday will be one of these. It's the rate limiting nullifier dApp that was authored by some friends at the EF. So on Wednesday, the guys, Tyler and Rasul, will come and talk about the code base. By that time, you will be familiar with CIRCOM, and we'll start from there. On Thursday this week, or maybe sometime next week, we will, as I mentioned, you can ignore like some of the difficult parts or difficult steps that happen after the loss reduction. This, you should, by Friday, it should be very, very clear to you. But things that happen under the hood, we will bring in hopefully 2 speakers next week to talk about trusted setup and pairing, which are things that happen under the hood. But for the sake of our audit, we don't have to cover that in details, but you should be able, hopefully, to understand the entire machinery that goes from a source code, an intent, we expressed an intent, which has this property, all the way to a bunch of polynomials, and then the machinery underneath takes care of producing a proof which can be verified in the smart contract. So with that, I'm going to stop today. Happy to answer any questions about this or about anything generally. I will today share the solution to the quiz that I told you about, the quiz from the biological sources. I saw some questions about it. Some very interesting answers. Like some of you guys got it almost right. You're on the right track, basically. Part of it, if you didn't get it completely, don't feel super bad, because the description is a bit sloppy. And I chose to, for example, not specify the optimization threshold that you need to optimize it towards. What are we optimizing for? I said as healthy as possible, which is kind of ambiguous, and I did that intentionally. But if you didn't get it completely, that's fine. At least the whole point for me was to get you to touch and feel this notion of, oh my, I have to pick a G. Which one? I do not know. Let's just pick one and see what happens, and so on. I just wanted you to internalize that notion of reduction. We will see you in the next session. Will be Wednesday with Rasul and Tyler. And I will share the solution sometime today. And when you're going through CIRCOM, feel free to ask any questions in the, I guess we can start asking them in the channel for module 2. I'm going to open it up today, and I can tag Russell and Tyler and other mentors who can come and help with that. So thank you, and see you guys on Wednesday.